Hi, welcome to another video. Today I'm pleased to bring you the code to initialize an SD card. So when I say initialize, from powering the card up to actually activating it so you can write some code to it with a microcontroller. So today is the 7th of October 21 and there are currently no examples on YouTube of how to initialize a card without using someone's library. And then even when they do use a library, they don't go into the raw code and the SPI commands. Now I've just released a series of videos showing how to access the data on the Fat16 and Fat32 file systems, including the Fat32 on a USB. I've spent many months, so I hope you appreciate that, many months and in 13 hours yesterday getting the timing right to initialize the card. 2 gigs is plenty big enough for a microcontroller. 2 gigs, that's 2 billion bytes. If you've been trying to initialize a card with raw SPI, you'll appreciate there's thousands of different pages on the internet and they all say something different. If you read the data from the SD card association and you've been trying to initialize a card yourself, one of the routines is to send a command 41 to the card. Now one flowchart, which I'll show you on the computer in a minute, one flowchart says you send a command 0, resets the card, then you send it an 8, then you send it a 41. And the flowchart keeps on saying if you get anything but a 0, keep on sending the 41. This is the sort of stuff I've had for months and months, other than timing issues and totally odd results here. I'll show you all the details, so don't worry. You have to be semi-familiar with trying to initialize an SD card using SPI, otherwise this 41 will mean nothing. But the SD card association say if you send a 41, that is a hardware specific command and it has to be preceded with a 55. So I took out my 55, did as the flowchart said, keep on sending 41 until you get a 0. Well, you keep on sending 41 without a 55, this is what you get, and the card will not initialize. And there's tons of garbage on the internet. So I will show you on the computer my raw C file using SPI how I got my cards going. So let me take out this bug by simply sending a 55 to this 41 first. Right, so I took out the loop that bypasses command 55, so the card powers up, you send it command 0, which resets the card, then you send it command 8, then you send it command 55 prior to sending command 41, then you can have a look at the voltage specifications if you wish, which is command 58, and then you're ready to read the sectors. Now reading sectors is command 17, but before you choose to read a sector you can tell it, you can go to command 16 to tell it you want to read a chunk of 512 bytes. These numbers here in magenta, that's spelling out FAT, the 6 numbers here, 49 to 54. So 6 numbers, that means this is Fat16, because I forget which card I'm using. So this is Fat16, I'll unplug it, plug it back in and let you see the boot process. Before I power it up, you'll notice as it runs through the commands, I'll point them out on the screen, it has to send 55 and 41 twice before I get a 0 from 41. 0, command 8, command 55, 41, and we've got a 1, 55 again, got a 0, voltages, reading the sector. So that was reading the last 100 bytes, this is now reading the first 100 bytes, starting at 235. and my loop, I only wanted it to do this once, but it seems to do it twice. So remember Fat16, look them up on the ASCII chart. The last command was 17, read the sector, which is sector 0, boot sector, and it's finished. So my screen capture does not like text on top of a display, on top of background pictures, and so that's why we've got these lines behind here. So now I'll plug in a 2 gig card formatted to Fat32. Unplug the card. Right, 2 gig card with Fat32. Zero, 8, 55, 41, 55 again, 0, 41, 58, 16, 17. And now notice these numbers are different. So that says Fat, F-A-T, and if you look 5 and 1, there's only 2 numbers there. That is actually 32. So 235 is the first number of the boot sector. I'll show you on the computer. 235, and if you've seen my Fat16 and 32 videos, you will know the boot signature is 85 and 170, which is actually AA55. If you haven't seen my other videos on the Fat16 Fat32 file system, this boot signature will mean nothing to you. This is page 59 of the SD card part 1 physical layer simplified from the, you should see the watermark SD card association, and it clearly says there send 55 before you send 41. So that flowchart I showed you, so keep on hitting the card with 41, it's not correct. Have a look at the C file when you've got a moment. Every command, bit 6, has to be set to 64. So if I show you Windows Calculator, so 64 decimal, you can see bit 6 is set. So if you want to send a naught, 64 plus naught, 64 plus command 1, 64 plus command 41. So if I actually show you, you can either go 41 odd with decimal 64 equals 105, or you can just use this define. So we are actually sending 105 for 41, bit 64 plus 41. If you're not familiar with binary and hexadecimal, you clearly haven't watched my other videos. So I am using today command 0, 41, 55, 58, then 16 and 17. Lots of variables. Some are being used, some aren't. Here is my buffer to receive the data from the card. So it's just a char, 512 bytes. I'm setting the bus speeds. Now this is actually a PIC32 MZ microcontroller running at, I think, 224 megs. Now the bus for the SPI runs at that speed divided by 2. So if you look at my initialize SPI, so to start with, this is my SPI. I'm dividing the clock by 280 times. So 224 megs divided by 212 megs, divide that by 280 gives me a clock speed of 400 kilohertz, which makes the system compatible with older cards. Apparently that's what you're meant to do. Later on I pick up the bus speed and divide it by 8. So there's a little note here. It was here to remind me in the beginning. I mean, I don't need it now because I've been on it for months. So every command, if I show you command 0, chip select equals 0, there's the command 0, which is software reset. Here is a 32 address, and then followed by a checksum. And most documents on the internet is actually right. The first command, command 0, you have to have the right checksum, 95. But what's also important in this checksum, that last number, let me pull this calculator up, programmer, right, hexadecimal 95, right, notice this last least significant bit is a 1. The 1 is a stop command. All these other 6 bytes are the checksum. The 1 is a stop. So with that stop in mind, so there are the 6 bytes you have to send with every command. Now when you send the command, you have to give the card time to respond. Now for months I had my delay, this response time, I had them all outside of the chip select. So if I take this out of there just so you can see it, cut, I was doing this, chip select 0, command, 32-bit address, checksum and chip select off, then putting the waiting time here. It could be 1 or 2, I think the specification is up to 8. So this is what I was doing for months. I was not getting the right results for the card to initialize. Now accidentally I hadn't turned off the chip select here. So some of this data was being sent whilst the chip select was still low. So sometimes I was actually getting the right result from command 0, not any of the others. So then I started messing about with these delays. So these are just delays, nothing else. Bearing in mind the checksum bit 1 is a stop. You can write something else within the chip select and it's ignored because it's already got the stop there. So I've 13 hours of work yesterday moving all these delay bits about. It's a command response time, just writing another dummy byte. I sussed, put 1 byte in here and sometimes have 1 outside and sometimes not. The card started working. So there's my command 0. There's loads of loops because I was jumping from command 0, then trying 1, then jumping over 1 to loop 2, which is command 8. And you'll see it got consistent. I start, write the data there. Before I de-assert the chip select, so turn it off, I put another wait within the chip select. So within that time, and it makes a big difference. You start getting the right results. So depending on what age cards you've got, just mess about with the timing if this file does not initialize your card. Now what the SD-Karte Association also say is with every response they say there's either 6 bytes sent out or something like 128. But you might have seen, if you've been dabbling already, you get a response 1, 2 or 3, meaning 1 byte, 2 bytes or 3 byte response. That's not totally correct, but so for a long time I was actually reading 6 bytes from every response and then displaying them here. So I've done loads of tests because I don't want to upset the thing. This command 8 is sending 4 bytes that you need to read. This is the bit where it's version check and checking the voltages. And if command 8 is sent correctly, this is known as an argument or an address. When you initialize the card, it's an argument. The argument for command 8 is 1AA, and it sends back 1AA. if it's been accepted. Now for a long time, because I did not have this in the brackets, I was getting 128, then 1 AA, then something else. Put a delay within the chip select, I started getting 0, 1 AA. So it's critical where you put your delays. So command 0, and then look, it says go to loop 2, so I'm jumping over command 1, loop 2, sending it command 8. If data buffer is 0, so the first response is equal to 0 after command 8, I'm speeding up the SPI to what you saw earlier and going to loop 3, which loop 3 is actually underneath. So you can see I had been going to loop 4, and this loop is the loop I put in to bypass 55 to show you if you don't send 55 before 41, you will not get a correct response. And at number 5 you saw flashing on the screen at the beginning, there's some data on the internet, it says 5 means you've got a really old card. No, 5 means you're doing something wrong. So command 55, that's the SPI, a dummy right there and a dummy right there. Have a look at the C file, not all commands need dummy rights. Here's the 41, that does seem important. 41 and the argument, or you can see it's 40000000, and then checksum. Most of the checksums can actually be anything, but so long as the last bit ends in a 1. So you see this 41, I can delete this. You can see I've commented this one out. So 41 did not need an additional delay after the chip select was turned off. Then you can see I turn the chip select back on, read the byte, turn chip select back off, just display the number. So that's 41, loop 5, so 58, displaying the data, command 16. So if you've seen my other videos on the FAT file system, you'll know that hexadecimal 200 is 512 bytes. So I'm telling the card I want 512 bytes in every read. So that's command 16. And same again, you see I've got one delay before I deassert the chip select, and I've commented out the delay after. So I'll leave a lot of the commented out stuff in the C file, because you might need to play with it if you've got different cards and it doesn't work. So after I've said I want 512 bytes, we finally come to some code that actually does something. So command 17 is read block. I must have hit enter and messed up the code. This is where I'm reading the block. I'm reading the boot sector, which is sector 0. So I've got a 0 here. So now this argument becomes an address. So this is command 17, read block, and I'm telling it read block 0, or the boot sector, which is sector 0, a block being 512 bytes. No additional delay again, just one inside before the chip select is turned off. This is reading buffer 86 and buffer 57. And you'll remember from my Fat16, Fat32 videos, depending if it's Fat16 or Fat32, it will tell you at these locations. It will say Fat16 or Fat32. So depending on which one it reads, it displays them here. But that's also important because when you read a whole sector of 512 bytes, this 17 also spits out a checksum or some sort of code before your 512 bytes. When you read back your 512 bytes, you don't start in your 0 to 512. You start with an offset, and it's either going to be 3 or 4 bytes. This one is reading the boot sector from essentially 0 to 100, but the one above it is reading from 416 to 512. Now if I open that HXD editor, as described in my previous videos, go to this SD card. So the one I last looked at, Fat32. Okay, right, so the first number, EB, Windows calculator, hexadecimal, E, B235. You saw that on my TFT. And the last numbers, 55AA, so decimal, actually hexadecimal. 55 is 85. And the last one from my memory was 170. So if I type in 170 AA. So I was reading the beginning of the boot sector and the last 100 bytes of the end. And it didn't matter if it's a 2 gig formatted in 16-bit FAT or Fat32. The initialization was the same for both cards. And once you've got the initialization and you can read sector 0, you can find all your files, including the root directory. Give me time to clean up that C file. It runs a clock and a display. The display hasn't been working properly because I haven't put any pictures on the card, just wanting the raw data and trying to initialize the card with raw SPI. Hopefully you'll appreciate, now you know you have the tools to initialize an SD card with no library. I have not used a library today. Not used a library to initialize the card, nor to read the sector. It's just some simple SPI commands. But the simple has taken me months and months to get working, because that timing and where you put your delays is critical. The delays giving the SD card time to respond. So have a look through the C file, adapt it to suit your needs. I'll put a link in the show more on GitHub. I'll also put a link if you want to donate a coffee or more for my time developing this code, establishing how it works and getting it to work and showing you for the first time on YouTube, because no one else has. If you do happen to leave a donation, you'll get mentioned in subsequent videos. So yeah, if you want to support my work and me helping you, that's how you do it. Just click on the link in the show more. Hopefully you've learned something. Thanks for watching.